In EKS, your application is not directly exposed to the internet. Traffic usually crosses AWS networking layers, Kubernetes routing, and then the pod before the container ever sees a request. That is why EKS networking confuses people. They mix up the load balancer, ingress, service, pod IP, and node IP, even though each layer solves a different job. If you miss one layer, you can create the wrong security boundary, the wrong health check path, or the wrong production troubleshooting story. In this tutorial, I will connect the whole model: Amazon VPC CNI, services, ingress, the AWS load balancer controller, security groups for pods, network policies, EKS endpoints, and private AWS service access. Amazon VPC CNI is the plugin that gives EKS pods IP addresses from your VPC, so pods participate in AWS networking instead of living on a separate overlay network. A node IP belongs to the worker node EC2 instance. A pod IP belongs to the individual pod. The scheduler places pods on nodes, but traffic often targets the pod IP that the node is hosting. Because pod IPs come from the VPC subnet, subnet sizing and IP management become production concerns. A busy cluster can fail to schedule pods simply because it runs out of usable addresses. Core DNS then gives the cluster a stable naming layer. A pod may move, restart, or get a new IP, but other workloads can still reach a service name without caring which pod instance changed. A ClusterIP service is the stable internal front door for a set of pods. It gives clients one virtual address and one DNS name, while Kubernetes keeps the backend pod list moving underneath. A NodePort service opens the same port on every worker node. It is useful as a simple exposure mechanism or as a bridge for some controllers, but it is rarely the clean production interface you want users to hit directly. A load balancer service asks AWS to place an external load balancer in front of the service. In EKS, that often means a network load balancer for layer 4 traffic, depending on controller and annotations. Ingress sits one layer higher. It is an L7 routing contract for host names, paths, TLS and HTTP behavior, but it does nothing alone until an ingress controller turns those rules into working infrastructure. In EKS on AWS, the AWS Load Balancer controller is the component that reads Kubernetes Ingress rules and creates an application load balancer with the right listeners, target groups, and health checks. That is the key interview answer. The Kubernetes application is not directly exposed. The controller creates the ALB from ingress rules, and the ALB forwards traffic towards services and pods. A typical public flow looks like this. The user resolves a Route 53 record, AWS WAF filters the request, the ALB accepts it, the ingress rule selects the backend, the service resolves endpoints, and the pod delivers the container response. When you understand that chain, troubleshooting gets cleaner. DNS issues live at Route 53. Layer 7 blocking can live at WAF or ALB. Backend reachability often lives at the ingress, service, readiness, or pod layer. A strong private EKS production pattern keeps worker nodes in private subnets, runs application pods on those private nodes, and only places the application load balancer in public subnets where internet-facing entry belongs. The ALB does not need your pods to be public. It just needs a permitted path to healthy targets. With the AWS Load Balancer controller, that usually means forwarding to pod IP targets or node-backed targets inside the private cluster. Your data tier stays deeper still. RDS belongs in dedicated database subnets, not beside the ALB and not loosely exposed to the rest of the VPC. The EKS control plane endpoint is a separate decision. A public endpoint allows API access from outside the VPC, with tight controls, while the private endpoint keeps Kubernetes API traffic inside VPC-connected networks. Private cluster networking is only part of the story. The workloads still need AWS services. For image pools, EKS nodes and pods commonly need the ECR API endpoint, the ECR DKR endpoint, and S3 access for image layers. That is why many production EKS designs use interface VPC endpoints for ECR and a gateway endpoint for S3. Secrets Manager, CloudWatch Logs, KMS, and often STS should also use interface VPC endpoints when you want private AWS service access without sending those calls through NAT. This is why private EKS architectures often have more endpoints than teams expect. Private nodes still need to pull images, fetch secrets, assume roles, emit logs, and talk to control services even when they never browse the public internet. So the production answer is not private subnet plus NAT by default. It is private subnet plus the minimum deliberate endpoint set, with NAT used only where there is a real requirement. Security groups for pods. Let specific pods get their own security group policy instead of inheriting only the worker node boundary. That matters when one namespace needs tighter north-south or service level control than another. Network policies solve a different problem. They control which pods, namespaces, or CIDR ranges may talk to each other at the Kubernetes network policy layer, so east-west traffic is not left wide open by default. Use them together, not as substitutes. Security groups align with AWS network controls and external destinations. Network policies align with pod-to-pod intent inside the cluster. The production warning is simple. If you run EKS without IP planning, readiness health discipline, security groups for pods where needed, or network policies, the cluster may work in a demo and still fail your real security review. If you compress the whole model into one sentence, EKS networking is the handoff between AWS infrastructure reachability and Kubernetes service discovery. Pods get VPC IPs from Amazon VPC CNI. Services provide stable discovery. Ingress describes HTTP routing. The AWS LoadBalancer controller turns those rules into an ALB, and the ALB drives traffic to services and pods. A clean interview answer sounds like this. In EKS, the Kubernetes application is not directly exposed. The AWS Load Balancer controller creates an ALB from Kubernetes Ingress rules. The ALB forwards traffic to Kubernetes services and pods. Worker nodes run in private subnets, and AWS service access should use VPC endpoints where possible. If you want to design safer clusters, think in flows. Internet to ALB, ALB to Ingress, Ingress to service, service to pod, pod to AWS services through endpoints, and pod-to-pod traffic through explicit policy. Subscribe for more practical AWS, Kubernetes, Terraform, and cloud engineering breakdowns.